So welcome all to the fifth and the final day of the summer school on data privacy. It's been a very engaging school so far, and so today we have like two very exciting lectures. You will get to hear about the experiences from the speakers working on real world projects as far as the privacy is concerned. So I myself personally am eagerly looking forward to the talks. So we have with us today Dr. Abhay Sharma and Dr. Anshoo Tandon from both from IISc. So I request our volunteers, Chaitanya Manas, to formally introduce the speaker, please.
So first I'll be introducing Dr. Abhay Sharma. Dr. Abhay Sharma obtained his PhD from IISc-Bangalore in 2015. And prior to that, he obtained his MS in Electrical Engineering from the Ohio State University, USA, and BTech from BITS Pilani. He has over 2 decades of experience working at Motorola, Bangalore, Analog Devices in the USA and Bangalore, and later at Algo Embedded Systems, Bangalore, where he worked in the area of high-performance video signal processing and emerging personal area network wireless technologies. Currently, he's also the CTO and Vice President of Development at the IUDX unit, SID, in IISc Bangalore. Dr. Anshoo Tandon is a Senior Research Fellow at the IUDX unit, SID, in IISc. Dr. Tandon obtained his PhD degree from National University of Singapore, advised by Professor Mehul Motani. He obtained his ME degree from the Indian Institute of Science, Bangalore, India, and BE from Kumaran University in Nainital, India. He was a research fellow at the National University of Singapore. His past industry experience spans over 9 years, where he's worked in lead or senior roles with telecom semiconductor companies such as Broadcom, ARM, Freescale Semiconductor merged with NXP, and Analog Devices on design and implementation of efficient and optimized transceiver algorithms for cellular and wireless connectivity solutions. His current research focus is on privacy, security, and probabilistic graphical models. His research interests also include information theory, coding theory, and statistical signal processing.
So thank you, Chaitanya. Now over to the speakers.
Okay, thanks, Chaitanya. Thanks, Vivek. I would like to thank again the summer school and IIITB for extending us this invite. I'm very happy to be here. And I will be talking a little bit about IUDX as well as I think some of the privacy related stuff that we are doing with IUDX. So I think let me just get started. I'll just share my screen. Vivek, let me know if you're able to see it as well as I'm audible, right? So,
oh yeah, clearly.
Cool. Okay.
Oh yeah. Yes.
Okay, great. So let me just get started then. So I think the talk again is titled Incorporating Privacy in IUDX, and primarily it will be led by Dr. Anshoo, who will be talking in much more detail about the specific techniques. And I think I will be giving an introduction to IUDX as well as I will be segueing into how privacy and what are the various privacy goals as far as that data exchange platform is concerned. Okay, so let's just let me get started then. So in terms of data, we talk about data smartness, and essentially it's a fairly generic term. And what do we mean by that is basically that we want to use data in terms of decision making. We don't want to be reactive, but we want to be preventive, for example, in terms of operations. Similarly, in terms of policy making, we want these inputs to not coming from one sector, but from multiple sectors based on data from various sectors. And similarly, the governance, we want to move towards evidence-based, participative, transparent kind of governance. So these are the various things we all talk about when we talk about data smartness. We want data to actually enable us to do all these things. And we also talked about, again, in the same context, we talk about data empowerment. Basically, so much data is being generated. I mean, in our cities, we have sensors, we have cameras, we have the citizen apps, and then we have even crowdsourced apps, utility records, GIS data. And so all this data, what is the we want to realize the potential from these. And of late, of course, there has been a huge uptick in terms of the machine learning algorithms, the real-time analytics processing is very much available. Cloud has enabled us to do so many things, right? So all these AI/ML as well as the processing can be actually salvaged to solve all these challenging and very complex problems that are there in the urban scenario. So basically, today smart cities around the world are striving to be data smart, right? And uh, I would just extend it to not only smart cities, actually various ecosystems, service delivery ecosystems are trying to be data smart. Now, we have noticed this, and this is not only in India, that the data potential is falling short. We are not able to use so much data that is being generated because data has been generated for some time. And again, if you analyze, the primary reason is there are a lot of data silos. The solution and the data silos again have come up naturally and because the key intent is to solve a problem. So what people do is they will go ahead and deploy a solution vertical and to tackle a key problem that they're facing. So urban mobility people will go ahead and put trackers in the bus, right? Because that's what helps them solve that problem, to solve ETAs. And similarly, somebody else will just go ahead and put based on their particular problem that they're facing, right? So now, what happens in all this is that the data sharing is not incorporated as a basic design principle. It's an afterthought, and many times it is very hard to actually then enable later on. So part of the problem, again, to break data silos is that the interfaces have been very non-standardized, right? Like there is no one APIs generally. The data models are all over the place, even for same type of the data. And this leads to very harder application development, right? Like think of an application developer was to make 100 API, different type of API calls to get data. And then not only that, the data models are different, and then it all becomes very hard. And of course, the data interpretations and the interoperability issues exist. Data interpretation means that you're not able to really use the data because you don't know what format it is coming on, what are the units also many times, and these are the issues why this data potential is falling short. And again, like a generic data exchange layer with standard interfaces can address the above concerns, and that is where IUDX sort of came in. And in our urban scenario, it started off as an academic project in IISc, and then later onwards, Smart Cities Mission within Ministry of Home and Urban Affairs picked it up, and then we together worked in a collaborative fashion along with various other academia organizations as well as the private organizations to conceptualize and build this platform. So what is this platform? Actually, on the base, it is basically a data exchange platform, open source. And what we have done is that if you see at the bottom, there are a lot of public, private data sources. And what we've done is that we have put in a layer in between, a middleware in between, which helps the applications and use cases who are generally decoupled from these data providers to actually get this data in a very seamless fashion, right? So there is catalog server, which is the data exploration plane where you can discover data sources. Then there is an authorization and consent server, which allows you to actually get access to data which is not open. And similarly, finally, there's a resource access service, which finally delivers data to you. So I think these are the three main components of IUDX. These are all deployed currently in cloud, and everything is, by the way, open source. And the current charter is to handle non-personal data, but we are looking at hooks for the personal data also, because such data does exist even in the urban domain, right? And but the key things here is the data is going to be served, discovered, and authorizations for it can be had through standard APIs. And when the data is served for you, it will be through open and sort of harmonized, standardized data models, right? So again, where we think that this exchange can take us. Actually, exchange is not a solution in itself, right? Remember, the ultimate goal is to be able to develop applications with that data, because that is what's going to deliver the value. But the exchange is definitely going to accelerate all these things, and that is what we call that it is going to lead to a data space around an exchange, right? Where you have, of course, there is a data and analytics application going to consume the data, but then there will be for a given domain or for a given application vertical, there will be some kind of an app ecosystem, there will be data models, and very important, there will be some kind of data policy and economics kind of guidelines that are coming in. All this can feed into a data exchange, and again, so it will lead to then important insights and lead to a good service delivery. As I was saying, lead towards the data smartness goal that we have. Right. So and then the hope is that currently we are doing this for the smart cities or the urban space, but then I think tomorrow this can be replicated across verticals, right? Agriculture or maybe mobility. Mobility itself can be a very separate vertical. So all of this can then be replicated. The framework can be replicated, and again, initial indications are from field that yes, exchange will play a very important role in all of this. So just again, now I would basically, this is more about the data, and I just want to just say that currently it is in production deployment, and we have close to 7 data coming in from 17 cities, and many more. We hope to get it to 25 this year, and then I think the hope is to keep on expanding this footprint, and the use cases of the data comes from mobility, domain, safety, traffic, flood, waste management, air quality monitoring data. All this is the data which leads to these kind of use cases. And actually, the approach for IUDX has also been that the data, we go along with the solution developers to the cities, and a lot of these use cases are being developed in partnership with the cities, so that not only the data, like we can also sort of bring to the table the value of this data, the value of this data, and some use cases which the cities can make use of, because they have so much data and something needs to be done properly with with that data, right? So currently now what is happening is that we have the best practices for security and privacy. Privacy in the sense that we are only giving data to whoever has the right authorizations. But I think there are some very advanced security and privacy techniques, and currently we are doing one project with NSC, National Security Council, and we are exploring some frameworks for how do we incorporate those mechanisms into IUDX. And today's talk is going to be about that. What are the specific things that we are looking at? But before that, I just want to give that when we look at the data, it comes from raw data to the insights that we derive. It may go through data exchanges, it may go directly from a provider to consumer. There are this is the kind of a journey it takes, where you collect the data from subjects, sensors, and web scraping, and all of this. You make sure whoever is collecting it, they follow the right privacy policies. But once that data is coming into a system, it is going to sit with the data custodian per se, or we also call it provider. And then after that, the data can be shared for computation from multiple data sources, or it can also be, for example, shared, offloaded. The computation analytics can be offloaded to the cloud, and finally you derive some good insights out of it. You do some kind of inferencing on it, you process it, and these insights are going to be then distributed to finally people who are going to use it, right? Citizens, government policy making, and all those things. So that is what we call as the result parties, and in between are the compute parties, which could be collaborative compute. And this is roughly, I mean, I mean, I have put in this order, but some of these blocks can also be interchanged. But generally, it will be following a very similar journey. And in this journey, why I put it up, because we want to identify that there are different states in which data is, and as far as privacy is concerned, we want to identify which states these are on and what are the privacy goals during that, right? So, for example, the leftmost state, we have data at rest. The data sitting with the custodian. Now you need to prevent any security breach there, because any secure breach can lead to, again, privacy infringement. Then similarly, while sharing it, sending the data to different to cloud or to another IT system, it will be in transit, and again it needs to be protected because it's out in the wild. So both these data at rest and data in transit are sort of well understood, well established techniques and frameworks exist. We understand the best practices, the loopholes, all of these we understand, and I think in some sense in IUDX these are already incorporated also, whatever relevant one. So we're not going to look at these two because they have been already, as I said, fairly mature. Now, even if you do encrypt data at rest and in transit, at the time when another server is having a look at it, you're processing it, you're gonna open it up, you're gonna bring out the data and clear. Now at that point, attacks can happen, and that is what we need to protect also, because these days a lot of computation happens in third-party servers. It's no longer my server. You go to a cloud, you go to a collaborative compute server. So the data has to be brought out in open at that point, and that is what we call as, that state is called data in use. It has to be protected. The data has to be protected there also. And basically, this is very new and challenging frontier, and we are going to talk about this. And finally, when we talk about that, okay, all these things are happening, and then you have finally derived some insights after some processing. This processing can be anything, okay? It can be very simple, say simple averaging also, or it could be a very complex inferencing through neural networks, deep neural networks. But once you release the outputs, and it is being released to an intended audience, do we still think that there will be no privacy leak? And the answer is no. There can still be a way back from these outputs, back to somebody can derive some information about the inputs, and there are many ways to do that. You can get hold of some kind of a side information. You can get hold of some kind of side information all the way in the future also, and which can lead to re-identification, right? And that is what we call data post-use, and that is also something very interesting and very challenging. People are asking more and more protections in that space also. So we're going to talk about that also. So data in use is also called input privacy, and this output data post use is also called output privacy, right? So again, that same picture, I've just sort of, in that picture, I've just put in data at rest, data in transit, data in use, and data post use. So these are various places where we need to fortify ourselves, right? And so when we talk about input privacy, we are going to talk about trying to secure data in, as I said, in the cloud or in the collaborative compute platforms. And here we talk about trusted confidential compute and trusted servers, and it's also called secure enclaves. We also talk about secure MPC. We also talk about fully homomorphic encryption, SHEs, zero knowledge proofs. All these fall in this category of input privacy. I have just kept these two because these are the two right now we are working at. And then on the output privacy side, people talk about various anonymization techniques also, like k-anonymization, L1 diversity, and differential privacy. And I have kept differential privacy because that is one thing that we are looking at as a part of this project, right? So just bear in mind that across all of this, there is another very important thing, which is the data access policy enforcement. And if we have to be cautious, we have to be careful. We only release data to people to whom it is intended for, and through access control mechanisms. And there is a lot of work going on there also, and we have a project here which I'm not going to talk in today's talk, but Professor Srinivas in IIITB is looking into these kind of things where we talk about extensible and scalable consent frameworks, right? Because in a diverse environment such as smart cities, there is a lot of decoupling between providers and the consumers. And I mean, we need to talk about the consents, and needs to be very scalable and need to be extensible. There may be some future consent mechanisms that will be coming. So this is the picture, and specifically we are going to talk about TEE, MPC, and differential privacy. And I will take a couple of more slides and talk a little bit more about secure enclaves, because that Anshoo is not going to cover. But I think DP and MPC Anshoo is going to cover in detail, so I will be very quick over those slides. Okay. So secure enclaves, basically, it's also called trusted execution environment, protects data in use by computing, by offloading computing in a hardware-enabled secure enclave. Basically it's hardware-enabled isolated and hardened environment, right? And it basically, when we talk about confidential compute, basically we mean three things: that it provides assurances on data confidentiality, that it's not visible from outside, and of course by unauthorized actors, and it is the data inside the enclave cannot be altered by, again, from unauthorized, from somewhere from outside. And similarly, the code integrity, whatever is running inside the enclave cannot be modified by unauthorized actors, and any such modification is immediately flagged. We also talk about attestations, that is, if a request is coming in from inside the enclave, we should be able to attest that it is coming in from there, and that attestation should have some guarantees. And there are many other features, but I think these three that I mentioned, these are the main ones. And generally this helps us to achieve the kind of security for data in use, right? Now, why do we talk about hardware security? Because then I think with hardware, what happens is you have lesser layers. Otherwise, security has to be guaranteed by things sitting on OS, device drivers, platform providers. But here we don't have to trust. We have to trust as little as possible, and therefore the attack surface is vastly reduced, because it is all dependent upon the hardware, which sits at the lowest layer in this whole stack, right? And general techniques which people talk about here are inline memory encryption like Intel SGX and IISc, and then hardware enforced CPU memory isolation. And we also talk about code attestation and things like that, right? So use cases for enclaves is, again, you want to offload your workload to cloud environment, right? And you have a sensitive data. Most of the organizations do not want to do that unless such guarantees are available, because even cloud environments are not very trustworthy, right? So I mean, sometimes for the sensitive data, I mean, definitely they may not be trustworthy, right? So then multi-party computation, right? Like when you are, if you have an enclave which runs a known compute, you can run ML as a service where one person brings in data, one person brings in the data, and therefore a lot of such use cases can be enabled where the model provider doesn't want to release its model in open, and similarly the data provider, of course, doesn't want to release its data to even the person who's running the inferencing model. So this allows such kind of things, right? Similarly, training from multiple data sources, like say cab aggregators or various telecom providers, hospitals, they want to share data and learn a given model, but then they don't want really to share the data in open. So such, again, this is one way to do that. Another very exciting way we will hear from Anshoo about that is MPC. And I think in the summer school, we already had some very good sessions on MPC already. So again, I think the mobile computation, personal computing devices, all of these actually secure enclaves are coming. It's already existing. Secure elements are existing in your mobile phones, and you will see Androids and I don't know, Apple talking more and more about it in coming days. Again, I just wanted to give you a landscape. The cost of technology, right? Like, of course, technology is there, but currently, like this technology, of course, requires specialized hardware because that's what it is. So, but in terms of how quickly I can adapt to the applications, there are challenges. It requires modifications to existing applications. Applications have to be written in a way that can run inside the enclaves. And of course, these are slow compared to computations in clear because there's a lot of encryptions, decryptions going on. Also, there are hardware limitations. There are cache limitations. You cannot run like really high, like bigger neural net modules, for example. In terms of readiness, I think the understanding, theoretical understanding, and I would also say is highly mature. It's already out in the public, out in the production domain. Operational adoption is early stages. However, hardware platforms, there are many hardware platforms now in production. Intel SGX, AMD SEB, ARM Trust Zone, and similarly now, based on these hardwares, compute services are coming up more and more on enclaves like Azure. Confidential compute is there. AWS has Nitro enclaves. Google has confidential compute, which I think they released recently. And so the key challenges here are with each of this, there is going to be a sort of a slew of development tools required for an application developer to quickly port their applications onto this. And also some understanding needs to be there in terms of usage paradigms, like how does the provider send data to within the enclave, like what kind of encryptions and stuff like that. But that is all being worked upon, and at least we are fairly upbeat on this, right? So multi-party compute, again, I will skim through these very fast. Basically, data is broken in, like, this is like, you don't have to trust a third party like which is going to be like then single point of attack where multiple people, the goal is that multiple people are going to do collaborative compute. And I think the federated analysis approach of SMPC has many advantages. The data is broken into secret shares, so it is never out in open, first of all. And these two servers, unless they if they follow a certain protocol, the data will again be never out in open. And of course, in the federated computation of a known function, the function has to be known a priori. And some advantages here are, because earlier, if you have to enable such computation, both the providers will actually fudge their data, add anonymizations, make it noisy, right? But none of that is required. So I think it leads to improved accuracy of the learned models, right? So basically, the key thing is SMPC enables collaborative data analysis without, and it does not imply that sensitive data has to be shared in open. Without that, this enables it, and that's a big comfort to many of these companies who want to do such kind of things, right? Again, I will skip this. Anshoo is going to talk about it. In terms of cost of technology, I think the computational costs right now, it is a lot slower compared to computations in clear. And similarly, I think there's a lot of communication costs. Every process that we do requires there is some kind of communication between the computation servers, and that can slow down the whole thing. In terms of readiness, I think, again, theory is highly, I think we understand it. Researchers have been at it for close to 40 years now. Operational adoption is very, very early stages. Some early products are there, like ShareMind by Cybernetica, Key Management by CPR. There is some relational DB, which is again based on MPC. And but these products are just coming out. I mean, last 1 year or 2 years. And the bigger concern here is that the frameworks and libraries, which, say, for example, researchers can use, or even right, they are very few, but there are some. Motion 2NX, Secure NN, Secure ML. These are all there. Recently, I saw some. It is a TensorFlow encrypted, TF encrypted, where such frameworks are being incorporated within the TensorFlow framework itself. So I think everybody is working towards it, but that is where I think a lot of push is required. And I think keeping the fingers crossed, yeah. So finally, I think I will come to DP. Again, DP, because I think we thought MPC is anyway covered in the summer school. So DP is where we're going to talk a lot more. Basically, the guarantee of DP is that the recipient of a data release will make essentially the same inferences about any single individual's private information, whether that individual's private information is included in the input or not. Therefore, you get a plausible deniability, and therein lies your snuggle factor that you can say it's not part of this analysis, and that protects your privacy. Anyway, I think again, we will discuss this particular part a lot more along with the use cases. And let me just quickly talk about, again, I'm running out of time, that's why I'm hurrying through this part. We use it in two ways: analyst queries on private data sets. You keep querying on the private data set, asking for a certain statistics. The statistics are released to you with a certain noise, some fudge factor, and this noise is where the whole analysis comes in. And you also have to keep track of that. You cannot keep asking the same query again and again. There is some kind of a privacy budget which runs out, beyond which you are not given any data. In terms of technology landscape, I think there is an accuracy loss. So that is one concern. That's a cost, if you will. On the other hand, there is a kind of a trade-off between accuracy and privacy that can be achieved using DP techniques. I mean, the computational costs are not too concerning, though. I mean, there's just simple addition of noise. Analysis is what we have to do. Again, there's been a lot of adoptions, and not like US Census Bureau at least has indicated that they're going to release the census report with DP, and Google uses DP for sharing some statistics. Similarly, I think all these corporations which deal with personal data on personal devices have adopted some form or the other, right? So the general consensus is there that, you know, some kind of these kind of notions have to be brought in, and that is the hope that eventually it will lead to some kind of a unified framework. And the challenges still are there in terms of even theory. For example, we have realized that continuous release of statistics is a problem, and such release of statistics is very important, for example, for us when we want to talk about release of data, which is from IoT sensors, private IoT sensors and stuff like that. And establishing, like, general lack of understanding of DP is also very a little bit of a problem, because when we have to go and explain things to stakeholders like cities, it is a little hard to currently understand what is the meaning of that, some of the key parameters within DP, as Anshoo will explain. But anyway, I think work is being done to overcome these, and I said, when the technology gets adopted more and more, I think such problems go away. So again, to come summarize and put a final picture, I'm just saying that I've already told that data in transit and data at rest was already taken care of through well-established cryptographic techniques. Through this project, we are making some kind of an attempt to bring this to deployment, even in exchange, MPC as well as secure enclaves. In my opinion, secure enclaves would be the first as a part of the infrastructure, analytics infrastructure that can be provided along with the exchange and data, which will enable some kind of input privacy guarantees. And finally, in terms of when we release that statistics, we are looking already at output privacy through differential privacy. Differential privacy in general is, at least in the academic circles, is like, I mean, it's already established as a king that this is the best that we can do. Now the question is, how do we bring that out into the field? And that's a goal of in this project, and that's what we're looking at IUDX. So I think I'm going to stop here. I just want to acknowledge the NSC and Mahua, Government of India, who are our sponsors, our academia collaborators from IISc, IIITB, and I just put in my team members here. Yeah. So I can take some questions, but I can take questions later also. I'll be there. But anyway, if there are some questions, I can take them now.
Sir, the questions actually appear on the chat window. I can read them out for you.
Okay.
Can we use blockchain in cloud for data security and authenticity? If yes, then what difficulties we face in implementation?
We specifically haven't looked at blockchain use cases, but yes, it can be used. But the general understanding is that blockchain will be used for establishing immutability, and sometimes we feel that the kind of data we deal with, blockchain is like a very big hammer to go around with that. So that's why we have currently not looked at blockchain, but people do talk about within smart cities or within exchanges. People do talk about using blockchains for say maintaining smart contracts. So when you identify that this provider and this consumer enter into a contract, and then if those smart contracts can be run over some kind of blockchain tools.
Hi, this is Vivek. The one year, the model or the design architecture you showed on the last slide is very interesting. You know, combining FHE, MPC, or zero knowledge proofs with differential privacy, right? That. I mean,
Yes.
that sounds very interesting. But I just want to know how it works. You know, you mean some initial processing is done, the data is finally decrypted, yeah, and then DP is applied, or like what do you mean? Or you want to apply?
Yes,
On the
yes,
private.
yes. So the DP is typically where, see, DP is in some sense, it's the DP assumes that you are giving something to an intended audience, but then what can you derive based on the output? Whatever statistics you have given to them, is there any possible ways in which you can get? So DP will be used whenever we are releasing, instead of a raw data, we are releasing statistics on that. For example, just a use case, again, I'm not talking about the use case specifically from smart cities because that we don't have a very personal data. But for example, the health statistics. Supposing you are releasing a lot of health statistics about disease prevalence in certain regions, you want to, even if you are releasing statistics, averages, max, means, you would want to do that by using DP mechanisms, by adding noise on top of that, because it is clear that even if you don't do that, there may be attacks. There is a possibility of some side channel, some other information available to people some other time in the future, which they can use to infer some things about you, right? So that is where DP can be used. And for example, supposing in terms of how you combine this is, supposing two people have agreed together and they've done a collaborative compute to release a learned model, right? A model, a joint model which they have learned and released. Now that model, if it is based on, again, say some data which was sensitive, say again health data, or say private tax data, say private utilities data, then what you want to do is you want to release the model, a noisy model, so that, you know, again, from that model, sometimes you can construct what were the inputs. So that is where both DP and these other security enabling techniques can be used together. So that is what we are building. That's how we will use.
Yeah, that's very interesting.
Okay. Any other question?
So there is one more question, that is, what is the application of ZKP?
So I think this is again that we have not looked at it in smart cities domain, but in MPC, not MPC, yeah, in MPC literatures, zero knowledge proof, where you want to verify without giving some information. So for example, in auctions and other stuff, these kind of things are used. So I think there are some products on ZKPs now. I mean, again, we have not looked at it because we don't have those kind of applications. But if you look in the MPC literature, these auctions, auction kind of stuff is where ZKP is used. I don't know, Anshoo, you have anything more to add? You can add.
Yeah, nothing specific on this zero knowledge proofs.
Okay. I think Anshu, you have answered the TEE question. So actually, TEE versus cloud computing. I mean, I think basically these are again there can be some very minor differences, but again, I'm going to give a very systems engineer answer that this is just same. One guy is calling TEE, and then based on TEE, you can do what is called as a confidential compute. Right now, there are fights already in industry over the usage of term confidential compute. So there is a consortium which calls confidential compute, and they say confidential compute guarantees this and this and this in some certain ways. Whereas Amazon says, no, I am providing trusted execution environment, and I don't adhere to some of the principles in confidential compute. So I think it's basically nitpicking, but that's why I had used the term slash. But in some sense, if I would like to just give very simple answer, TEE is used to provide confidential compute with certain guarantees. Yeah.
Okay, so
I think I would. Yeah. Okay. Great. So I think I would then over to you, Anshu. So as I've already mentioned, so initially in our abstract we had put in something like where we would present both MPC and DP, but I think we realized that MPC is fairly covered in a lot of detail already in a couple of or maybe at least a couple of lectures in this summer school. So I think what we will do is we sort of realign. We'll give a slightly bigger session on DP, but then I think we are going to also cover MPC from implementation system point of view in terms of what we are trying.
So a very warm hello to all my friends and students. And again, thanks to Prof. Vivek for this invite. Dr. Abhay has given a very nice introduction about IUDX and the scope of work and the things that we do. I will be talking about two different privacy techniques that we adopt here at IUDX. The first one is differential privacy, and the second one will be secure multi-party computation. So we'll start with differential privacy. Right? Before we get into the details of DP, let's talk about few traditional approaches to data privacy. Right? So traditional approaches for preserving privacy, they are based on something called a de-identification technique, which could be listed as follows. The first one is suppression, where certain attributes could be completely omitted. You omit or erase certain attributes. The second one is generalization, where certain attributes may be generalized by replacing the actual value with an interval or a range of values. So for example, the PIN code of a person may be generalized by omitting the last two numbers of the PIN code. The third one is swapping, where certain attributes of a set of users may be swapped or shuffled amongst the users. The fourth one is aggregation, where the attributes could be averaged amongst the users. Now, what are the issues with these traditional approaches, and why are now people talking about a new technique called differential privacy? Right? The main issue with traditional techniques is that the data shared by a data provider or curator could be linked or combined with other sources of data to re-identify the attributes. This linkage attack can be performed not only with existing data sources, but also with future sources of auxiliary information. Now, this point is very important because it's very hard to control what could get released in future. You could have a release right now and take into account all the previous releases, and you can try to make it as secure as possible. But there could be some future sources of information that could be linked with your release to re-identify a lot of the attributes. There are many real-world examples of data releases that were thought to be sufficiently protective of privacy, but were later shown to carry significant privacy risks. The most important example is the reconstruction and re-identification of the 2010 US Census data. So there was a privacy attack on the 2010 US Census data. Researchers in 2018 revealed that the underlying confidential data from the 2010 US Census can be largely reconstructed. So note the difference in time. The census data was released in 2010 and the attack was carried out in 2018, which means the researchers were able to use a lot of the information that got released in between 2010 and 2018 to reconstruct a lot of the attributes that were hidden in the 2010 US Census data. So researchers were able to reconstruct with perfect accuracy the gender, age, race, ethnicity, fine-grained geographical location up to the block level for 46% of the US population. In fact, researchers also showed that if they slightly relax their conditions and allowed the age to vary by up to only 1 year, these 5 pieces of information could be reconstructed for 71% of the population. The details of this privacy attack are detailed in this 2019 paper that appeared in the communications of the ACM. It's a very interesting paper, and I recommend people to have a read. Okay, so there's a question here saying that isn't gender, race, etc. part of the census? Yes. So here the idea is the US census might reveal a population statistic saying that so many percent of people in this state have this gender, have this race, but they will not identify individuals with their specific race and gender. So what information is hidden is for your given name and your identity, the specific information about your age, your salary, your gender, your race. So as an aggregate, you might be having some information that in this state or this town, there are so many males, so many females, and so on. But for every given person, for every given name, the gender, race, these things will not be revealed. Okay, let's come to the next slide. So there are risks due to linkage of multiple statistical releases. Any research output increases disclosure risk. So this is again a very important statement. Although we have a lot of sophisticated techniques, there were some techniques that were being used previously, now we have DP. But even with DP, the idea is that any research output will increase disclosure risk. So it will lead to maybe a small amount of leak, but there will be slight privacy loss with each leak. And the main potency of this linkage attack is a lot of these small information, they can get accumulated to have a, it can lead to a point where you have a severe breach of privacy. So the idea is taken together, multiple releases can enable an accurate reconstruction of large portions of the data set as seen in the reconstruction and re-identification of the 2010 US Census data. Now we come to DP, differential privacy, and how it can solve this problem of linkage attack, right? Differential privacy is a very useful tool for protecting privacy that is robust against linkage attacks. So it doesn't say that, we completely avoid attacks. It's saying it is robust against linkage attacks. So DP provides a strong mathematical definition of privacy, protecting against the threats of unknown future attacks. With DP, statements about risk are proved mathematically rather than supported heuristically or empirically. DP is employed when releasing population statistics such as counts, averages, and histograms. DP ensures that the ability of an adversary to inflict harm of any sort to any set of people should be essentially the same, independent of whether any individual opts in or opts out of the data set. So this is related to the DP guarantee that Dr. Abhay talked about. We come to the DP guarantee. So this point is important, so I'll repeat it. It is basically, DP guarantee is basically a mathematically established guarantee that the recipient of a data release generated by a DP analysis will make essentially the same inference about any single individual's private information, whether that individual's private information is included as an input or not. In terms of a picture, we have the standard picture. We have an input database on which we perform some analysis, computation, and release a DP-enabled output. In the second row, we have the same input database, but now one of the users, say user X, has opted out, which means we remove all the records corresponding to user X from the input database. Now we perform the same analysis and computation and give out a DP-enabled output. Now, if we compare the output in the first row and the second row, if they are DP-enabled, then these outputs will be essentially the same. The difference will not be much. So the idea is that if the output does not change by removing the records of one of the persons, then through the output, it is very difficult to learn any information about that user. And because this user could be arbitrary, this means that just by looking at the output, it is very hard to infer any information about the private data of any specific user. So now the question is, how does DP work, right? A very top level simple answer, it works by adding random noise. To achieve differential privacy, carefully crafted random noise must be injected into the output. Higher noise leads to better privacy protection, but lowers accuracy, right? Intuitive. However, as the number of samples in a data set grow, the loss in accuracy due to noise addition in a DP release can become much smaller. So this sentence is important. I'll repeat it. It states that as the number of samples in a data set grow, the loss in accuracy due to noise addition in a DP release can become smaller. So now the intuition behind the statement can be seen in the following example. Consider two different scenarios. In scenario 1, we want to release the average marks of 5 students. To protect the privacy of individual marks, we add random noise to the output. Right? In scenario 2 now, we want to release the average marks of 50 students. In scenario 1, we have 5 students, scenario 2, 50 students. Now, to achieve the same level of privacy as scenario 1, the amount of noise to be added in scenario 2 will be much lower. This is because the contribution of any individual student in the overall average is much smaller in scenario 2. So in generally, as the number of samples in a database grow, we can have good protection of privacy by adding little bit of noise so that the accuracy is also good. So what are the strengths of differential privacy? Differential privacy is robust against release of external or future information. This is because your information is protected by noise. And the idea is, even if you remove one of the users from your input database, the output will not be able to help you in finding out very specific information about that given user. So DP provides provable bounds with respect to cumulative risks. As I said, every release will leak some amount of privacy. So DP is providing you with provable bounds with respect to cumulative risk from multiple data releases, and it is currently the only existing approach to do so. These privacy bounds are known as composition theorems. DP is also robust to post-processing. What does it mean? It means that any manipulation or transformation of a DP release cannot decrease privacy. So if you take the output, perform some transformation to it, do some noise addition, truncation, it will not affect your privacy. And the last point is that DP provides transparent tools that enables public scrutiny of its privacy techniques. So I can have a release and I can say that my release is DP enabled. I can also share you the code, the specific approach that I used to protect privacy using DP. But still, you will not be able to gain too much information about specific individual information from the output release. Now we look at a very simple case study. Suppose an organization wishes to release the average salary of its 100 employees. The HR department feels that averaging the salary will anonymize individual salary information, and it proceeds with the release without DP. Now consider the scenario where a different group within the same HR department decides to make another release without DP of the average salary after 1 month of the previous release. So now we had one release, and after 1 month there is another release of the average salary, and people think that because we are just giving out the average salary, the individual salary is protected. Now assume that one of the employee has left the organization within that past month. So in that interval between the releases, the first release and the second release, consider a case where one of the employee has left. Now you have the average salary of 100 employees and the average salary of 99 employees. Using that, the second release, the first and second release can help you reveal the exact salary of the employee who has left the organization. Here is that just the release of average statistics is not adequate for protecting privacy. We need to incorporate differential privacy by adding appropriate noise to the average statistics. Now we come to application of differential privacy in IUDX, and how do we use it? We apply DP to ITMS data from Surat city. So what is ITMS? ITMS stands for Intelligent Transit Management System. This data consists of records generated from transit buses operating in Surat city. The parameters reported by the bus include the following. So there are 3 useful parameters. First one is the license plate number. Second is instantaneous speed. Third one is the location coordinates, the latitude and longitude of the bus. Our goal was to release useful statistics about its data set in such a way that the privacy of the users, in this case the drivers, is not compromised. The architecture is as follows. Consider on the left side ITMS data of duration T. So consider this ITMS data for 1 year. So let's say we have this bus traffic data for 1 year for Surat city. What we do is we divide the ITMS data into batches of time duration T naught, which is, for example, 1 month. So we have a database corresponding to, let's say, ITMS traffic data from Surat city for 1 year. We'll divide it into batches of 1 month each. Now we take the data of 1 month and we divide the city area into hexagons. So for example, here you can see some images. These snapshots are for Surat city, and we are trying to divide this area into different hexagons. We also divide the time of day into time slots. And this combination of hexagon and time slots is what we call as hats. So if the hexagon ID is HI and the time slot is TJ, then the corresponding hat will be denoted as SIJ. So we release statistics per hat. What are the statistics? We reveal 2 statistics. The first one is the average speed across all the buses in that hat. The second is number of speed violations in that hat. So hexagons and time slots. So why do we use these hexagons and time slots? The hexagons help to anonymize data in the spatial dimension, and time slots help to anonymize data in the time dimension. Now the question is, how big should be the hexagon size, right? So bigger hexagon size will imply more buses per hexagon, and this will lead to lower privacy loss. So as we've seen earlier, as the number of samples in a database grow, the privacy loss can be made smaller by adding a reasonable amount of noise. We don't have to add too much noise, or if we are fixing the noise distribution, then if you have more samples, then the privacy loss can be reduced. However, if the hexagon size is too large, then the traffic information about hotspot areas with slow moving traffic might get lost. So although we want the hexagon size to be, fairly large, we don't want it to be large enough so that we lose information about these hotspot areas where the traffic is very slow, or certain areas where the traffic may be fast moving. So we don't want to club these different areas that could be fast moving or slow moving into one single hexagon. We want to have separate hexagons such that they identify regions that are fast moving and slow moving. Second, how big should be the time slot size? Again, bigger time slots will imply more buses per time slot and will lead to lower privacy loss for a given noise distribution. However, if the time slot size is too large, then the information about peak traffic might get lost. So for example, if we have a time slot size, for example, of 3 hours, then if you look at time from 9 to 12, for a time slot of 3 hours, then this may not be a great thing, because the peak traffic might only be from, let's say, 9 to 9:30 or 9 to 10. And because our time slot size is too large, we have lost that information. So we want the time slot size to be large, but not large enough such that information about peak traffic period is getting lost. The third thing is about selection of subsets of hats. Now, for a fixed hexagon and time slot size, there may be a huge variation in the number of buses operating over different hats. Right? Higher number of buses operating in a given hat leads to lower privacy loss. The worst case privacy loss will be due to those hats that have the least number of operating buses. I'll just stop here and look at if there's any question. Are the hats decided a priori? Are they changed dynamically based on various parameters? So, okay, very good question. So in our work, to start with, we considered a scenario where we fix the hexagon and time slot size. So we do a back calculation on how big should be the hexagon size and the time slot size and its impact on the privacy loss. And then we back calculate that, okay, we want the hexagon size to be large enough. So why do we want the hexagon size and the time slot size to be large? If it's large enough, then the privacy loss will be smaller. But if it's too big, the granularity of information is getting lost. So what we do is we fix a specific hexagon size and time slot size and try to work out the privacy loss. And if we feel that the privacy loss is reasonably small or little, is not much, then in that case, we try to reduce the hexagon size and time slot size such that the granularity of information is maintained. So we decide it once and it remains fixed. But this is a good idea where we could make it dynamic. For example, if we have a prior information that let's say traffic is higher in the morning time between 8 to 10. So instead of fixing the time slot to be 1 hour each, we could have an approach where for peak periods, we can have a granularity that's even finer. For example, the a time slot size can be made 15 minutes or half an hour. So one time slot will be, for example, 8 to 8:30, then 8:30 to 9, 9 to 9:30, and 9:30 to 10. This is possible, but we have not yet incorporated it into our system. The second question is, will the noise not affect the statistical analysis of the output? How is that dealt with? Again, a very good question. As we have said before, there is a trade-off between noise addition and providing privacy. So one approach is, you don't reveal anything at all. Then everything is private because we have not revealed anything. The other extreme is you reveal everything in clear. You do a computation and you feel that it is for public good. Even if it leaks privacy of individuals, I am ready to take that cost, right? So these are the two extremes. Differential privacy comes somewhere in between. It says, okay, I want to make sure that I make some releases for public good. At the same time, I want to preserve the privacy of individuals. Any individual information should not get leaked so that the person might be in trouble. So DP gives you that trade-off. So it says, okay, I will add noise, and it gives a mathematical guarantee that if you add, this much noise, how much is the privacy loss? So it gives you a correspondence, one-to-one correspondence, that if you add noise with a certain variance, what is the corresponding privacy loss? So there's a trade-off, and this trade-off, all the big companies, including Google, Facebook, LinkedIn, Uber, they are trying to grapple with it. They are trying to manage this trade-off such that they want their output release. So Google, whatever internet search we do, it is selling all our internet searches to advertisers. Now, advertisers want a very clear output. They don't want noise to be added. But that will be a breach of privacy for the users who have signed up with Google, right? So Google is saying, okay, we'll sell some information to the advertisers, but we'll protect individual information by applying DP. So there's a trade-off, but there's a word of caution here. All the companies currently, they do not agree upon what is the acceptable privacy loss. So one approach is they fix the privacy loss for users. They say that, okay, in a day, the amount of privacy leakage for a given user should not exceed a certain value. And then we'll add noise to make sure that the privacy loss doesn't exceed this value. However, currently there is no consensus across the companies on what is a good privacy loss number. Actually, researchers want a very small privacy loss. When they write papers and do things, we say that the privacy loss should be very small and all the big organizations should take care of that. But if the organizations stick to the recommendations of the researchers, then they will not be able to give clean outputs to the advertisers, and they are making money through the advertisers. So they add a little bit of noise. They allow the privacy loss to be relatively high. But researchers are also, kind of attacking the big tech for this approach, and they are saying that we'll try and come up with a common ground such that all the companies agreed on what is the acceptable privacy loss. Okay, third question. K-anonymity is also used in few papers for privacy provision, possibly an approximate variant of DP. K-anonymity is stating something as follows. So suppose I reveal some information that there was an accident at this place, right? If I want to release any further details, let's say I fix the value of K. So let's say K is equal to 10. I want to ensure that there could be at least 10 likely vehicles that could have participated in that accident. So for example, we want to hide the identity of the vehicle that was participating in a given accident. Now, around that time, if there are at least 10 or 15 vehicles which could have potentially participated in that accident, then I can release this information that yes, there was an accident at this place. But at the same time, in the news release, I protect the identity of the vehicle. Now, if the number of vehicles that could have participated is only 2 or 3, then I will not release this information that there was an accident at this specific place. Then I'll make a very coarse release that, in this area, in Malleshwaram, for example, there was a release, but which place in Malleshwaram, I cannot say. So k-anonymity is a good idea, but again, the problem with all these standard techniques like k-anonymity is that there could be future releases which you can use with this k-anonymized release, form a linkage attack, and then identify the specific vehicle that participated in this accident. So k-anonymity is a good standard technique that was used, but again, it doesn't protect us from linkage attacks which are released in future. So that we need to be careful about. For example, let's continue the same example of this accident. So let's say there are 5 different newspapers. They give 5 different reports about the same accident. It is possible that even if your news releases were trying to be, trying to preserve k-anonymity, if you combine all these 5 different news reports together, it is possible to identify the specific vehicle. It could be possible through some of the information that is getting leaked through each of these independent news releases. So DP is something that is done on top of standard techniques. For example, averaging, you can do averaging, but on top of that, you inject specific amount of noise so that you protect the identity of the individual.
Dr. Anshoo, should we know the queries in advance in order to protect, or we can do it on the fly, just like we do it for MPC? Oh, no, it may not be MPC, FHC, right? In the home encryption, we encrypt and we can do upright, any function later on, right? We need not decide it a priori. But does this happen for DP also?
Yes. Again, a very nice question. So in certain cases, when the data set is fixed, and the curator of the data set is deciding on what all information it wants to reveal, in that case, the queries are fixed by the curator himself. So, for example, if there's a 2010 US census information, right? They, at the time of release of the census, they decide that these are the queries we are going to release on the average statistics of the population in a certain city, in a certain municipality, in a state, in the country. So those queries are kind of fixed, but there could be scenarios, or the most important use case of DP is in the scenarios where the queries are not fixed, wherein an individual can go and ask. For example, if I am Google and you are, for example, an advertiser, you might want some very specific information from me about users so that you can have a very targeted advertisement for a group of users for your product. So there could be a scenario where the queries are not fixed a priori. In that case, the typical approach is we want to fix a privacy budget. We will say, okay, for every user, I want to make sure that the privacy loss doesn't exceed a certain threshold. Once I receive a query, I will answer that query by adding appropriate amount of noise. Once I have added noise with a certain distribution, I can compute the privacy loss due to that release. Now in future, if there are other multiple queries, I keep on releasing the information, being fully aware that the privacy loss of individual users is getting accumulated, the privacy loss is increasing. But DP gives me the mathematical framework through which I can precisely find out how much is the accumulated privacy loss. And once it reaches the privacy loss threshold, at that point, I stop taking in any further queries. I say, I have answered sufficient number of questions on this database on which these users were participating. Now I cannot give any further query because it will lead to a privacy breach, because the privacy loss budget has already been expired. Now I cannot release any further queries.
Yeah, thanks. That was interesting. Thank you.
Thank you. If you can question, please post on the window chat since you have. Okay, good. Thanks. Okay, so let me proceed with the selection of hats. So basically in our setup, we are saying that we fix the hexagon size and the time slot size, and we make sure that if we use this much hexagon size, this much time slot size, the overall privacy loss for users doesn't exceed a certain threshold. But there's a situation in practice, which is that for a given hat size, there may be a huge variation in the number of buses operating over different hats. So higher number of buses operating in a hat leads to lower privacy loss. So for example, if we look at the hexagon size, there could be certain areas that are highly populated. For example, there could be a school, an office. So there's a heavy traffic there. There could be other areas that are very sparse. So there's a huge variation in the number of, in our case, we are looking at buses. There could be a huge variation in the number of buses operating over different hats. The higher number of buses operating in a given hat lead to lower privacy loss. So we have seen previously, if you have more samples, then it leads to lower loss. The worst case privacy loss, that will be due to those hats that have the least number of operating buses. So there's some area with a very few buses, let's say only 2 or 3 buses. And if I want to release statistics about, for example, how many buses overspeeded, and the answer is 2, and there are only 2 or 3 buses, then it's kind of a privacy loss. So the worst case privacy loss will be due to those hats that have the least number of operating buses. We can limit the privacy loss by choosing only a subset of hats for which the number of operating buses exceeds a certain threshold. Okay. Now we come to the counting query. Okay, I see that I am running a bit short in time. So let me skip this slide and come to cumulative privacy loss. So the privacy loss, it actually depends on 2 important values. The first one is sensitivity. Sensitivity is basically the maximum variation in the noiseless query output when certain records of a user are replaced or omitted. And the second is the noise distribution. The privacy loss is directly proportional to the sensitivity and is inversely proportional to the standard deviation of random noise. We first compute the privacy loss per hat in our case. And then once we compute the privacy loss per hat, an upper bound on the cumulative privacy loss can then be computed by summing the privacy loss over all the hats. This is because we are releasing these queries for all the hats, and each query for every hat is leaking some privacy. So we can sum it up. So if n denotes the total number of hats, then the cumulative privacy loss is obtained by summing the privacy loss over each of the n hats. Now there's a slightly refined approach to computing the cumulative privacy loss. A more refined upper bound on the cumulative loss can be obtained as follows. As the first step, we compute the maximum number of hats that can be visited by any single bus in a single day. We call it M, for example. Then we sum the privacy loss only over these M hats. So this approach gives a slightly more accurate representation of the cumulative loss when M is much smaller than N. Now there are certain challenges in data quality. The first one is that there was a huge variation in the number of records reported by different buses. This perhaps can be attributed to different sensors fitted on the different buses. But rather surprisingly, there's also a high variation in the number of records reported by the same bus over different days. And these variations have to be taken into account when deciding on system parameters. Okay, there's a question. Do we get any better privacy on what kind of noise we add, Laplacian, uniform, Gaussian? Okay, good question. Typically, Laplacian noise is considered a very standard approach to adding noise because the privacy loss is a very simple function of the standard deviation of the Laplacian noise. We can add Gaussian noise also, that's not a problem, but we have to make sure, so in DP, we have to make sure that the support of the noise distribution should not be finite. So for example, uniform distribution is not a good distribution because the support of uniform distribution is finite and it can basically explode your loss. So this is not at all a good one, but you can use any a distribution, noise distribution, such that it has infinite support. Next question is, can it be said that release of data release of data itself cannot, it does not lead to privacy loss? For example, release of one average does not lead. However, when combined, yes, that is correct. And we want to protect our information against cumulative loss. Now, consider a jigsaw puzzle. Let's say there are 20 pieces in a jigsaw puzzle. If you put all those 20 pieces together, then you get all the information about a single user. But if the entire jigsaw puzzle is not fitting in properly, let's say you don't leak any information, right? Now in that setup, let's say you hold one of the pieces of the jigsaw puzzle and you release that information. Now you say, okay, I have not leaked any information, because just by looking at my piece of the jigsaw puzzle, you cannot get any information about the user. So that statement is not true, that you have not leaked anything. This is because you have leaked something. Now, if through some other source, if somebody else is able to get the other 19 pieces of the jigsaw puzzle, what it needs is your information to find out the details of a given user. So once your piece gets fitted, all the information gets leaked. That is why DP is giving you a mathematical framework. It's not going into the semantics on, okay, I'm releasing this average value. Right now, I think it is safe. Tomorrow, I don't know. It is giving you a mathematical framework that no matter what release happens in future, it is giving you a robust answer saying that I have quantified that this is the privacy loss with this leak of information, with this release. Tomorrow, if there's another piece of information, we only state that the privacy loss has now increased because of another release. It is possible in practice that all these different releases, as we have seen before, could be put together. So every individual piece of release of information does leak a little bit of privacy. Okay. So adoption of DP in the real world, Abhay has already talked about this. The US Census Bureau used DP for its 2020 census report. So they release this census report every 10 years. And after the fiasco in 2010, where a lot of information got leaked, in 2020, they used DP. Of course, Google, Apple, Microsoft, LinkedIn, Facebook, they all use DP. Again, there's no industry a consensus on acceptable loss, and continuous release of statistics remains a challenge due to accumulation of privacy over time. As Prof. Vivek asked, if their queries are not fixed a priori and users ask some specific questions, yes, you can release the answer, but every release will lead to a privacy loss. The privacy loss will accumulate, and once it eats up into our privacy loss budget, at some point we'll have to stop and say, now I cannot take any further queries. And I'll end with saying that researchers are hopeful that all these different companies will adopt common guidelines on acceptable privacy loss. So right now, different companies use different values of privacy loss. Okay. Here. So this is a list of references. The most important one is the third reference, which is a work from Cynthia Dwock, McSherry, Nissim, and Smith. This appeared in the 2006 TCC conference. This is a very useful paper, talks about establish the fundamentals of DP, and this paper went on to receive the 2017 Gödel Prize. Okay, now I'll come to secure multi-party compute. I don't have a lot of time, so I'll be very quick. Professor Ashish Chaudhary has already given 2 excellent talks on this topic in the summer school. So let me just run over. I'll not even talk about the basics. I assume that you would have attended those excellent talks and you're aware of the basics of the motivation on why we need to have secure computation. There are interesting techniques that could be used for secure computation. We have already talked about FHE. Is one of the techniques. In fact, there was a talk, I guess, on Wednesday on fully homomorphic encryption and how it could be used for confidential computing with multiple sources. Okay, so now, in this talk, I'll just quickly go through the secure MPC that we established using secret sharing. So secret sharing is, one of the SMPC tools for solving secure computation problem without a trusted third party. And this is basically a very simple example where we have three different parties. Party 1 has some value A, party 2 has value B, party 3 has value C. And let's say all the three parties want to compute the sum A plus B plus C. But they do not want the other party to know their own secrets. So example, party 1 wants to find out the sum, but doesn't want P2 and P3 to know the exact value of A. So this problem can be solved using additive secret sharing in two phases, the sharing phase and the reconstruction phase. So in the sharing phase, what party 1 does, so party 1 owns A, they will give out random values x2 and x3 to party 2 and party 3. Similarly, party 2 that owns random value, that owns value B, it will give out random values y1 and y3 to party 1 and party 3. Similarly, party 3 will give out random values z1 and z2 to A and B. Then what happens in the reconstruction phase? Okay, so now party 1, it has given out random values x2 and x3 to P2 and P3, and it owns A. So it can compute x1, which is equal to A minus x2 plus x3. Similarly, P2 that owns B has given out random values y1 and y3 to P1 and P3. Because it owns B, it can compute y2 equals B minus y1 plus y3. Similarly, party 3 can compute z3. So party 1 has x1, y1, z1, party 2 has x2, y2, z2, party 3 has x3, y3. They can all sum up these values, their own respective values. So P1 can get S1, which is x1 plus y1 plus z1. P2 can get S2, which is x2 plus y2 plus z2, and so on. Now party 1 can share this computed sum S1 with P2 and P3. Party 2 can share S2 with P1 and P3, and party 3 can share S3 with P1 and P2. Now, at the end of this operation of sharing the values as S1, S2, S3, all the three parties have access to S1, S2, and S3. So they can all compute S1 plus S2 plus S3. And it's not very hard to see that S1 plus S2 plus S3 is indeed equal to A plus B plus C. Sorry, is indeed equal to A plus B plus C. So all the three parties now have access to the sum, but no one party knows the exact secret input of the other two parties. In our architecture, we separate out the role of the data providers and the compute servers. In the previous example, the parties that own the data also were doing the computation task. In our work, we separate out the role of a data provider that owns the data and the compute servers where the actual SMPC protocols are executed. So data providers, they provide secret shares of data. They do not share the raw data. They provide secret shares to the compute servers. Compute servers execute a known function using pre-agreed SMPC protocol. In our case, we use the ABY 2.0 protocol. This is for a semi-honest setting wherein the servers do not deviate from the protocol, but could be curious. They might want to know more about the information about the other users. So anyway, in this ABY 2.0 will protect your information against a semi-honest adversary, and the final output could be revealed to the consumer. The consumers could be one of the data providers. The data provider himself could be one of the consumers also. So we come to the implementation. Okay, yeah, I have only 4 minutes, so I'll just say that we use the Motion 2NX framework for our computation. This basically Motion 2NX is a C++ software framework that supports two-party computation that we use. There are some implementation details that I'll not go through. The technology outlook, again, Dr. Abhay has already spoken about it, so I'll skip this. This may be of interest to the students. So this is, I've just put together a short list of startups that provide secure MPC solutions. So already here, like 7-8 startups are there that are providing secure MPC solutions. In fact, the third company, the Unbound Security, this organization is founded by Dr. Yehuda Lindell, who is an expert in the secure MPC field. So the future of secure MPC is very promising. In fact, IUDX is also hiring. So Abhay previously spoke about the scope of work at IUDX and the research activities we do and our work related to privacy and security. So IUDX is actively looking out for motivated BTech, MTech, and PhD students for internship positions. we are also looking out for recent graduates who can apply for full-time positions. And the focus of work is on privacy and security. The relevant areas are differential privacy, secure multi-party computation, and secure enclaves. Students can feel free to reach out either to Abhay or to me. These are our email IDs. Thank you. I can take any questions if they are there. Yes, Dr. Abhay is also there. So if you have any specific questions on IUDX, and so, I mean, just additional information for students, we are actually housed inside IISc, and we are working very closely with different professors at IISc and IIIT-Bangalore.
Sir, just curious, which cities, you mentioned Surat city, are there other cities that you're also looking at? Professor Abhay also mentioned 17 different places, right? Okay.
Yes.
Yes, we are close to currently in 18 cities, but yeah, I mean, each city sends its own different type of data. I mean, so we thought that this ITMS data, like the good data is coming from Surat city, and therefore we wanted to use that in our as a prototype for our experiments for DP. Actually, yeah, I mean, because I mean, that also serves as a very good proxy for data which may come from, say, floating car FCDs, floating car devices, like the data from cab aggregators, or sometimes even from ambulances. We started to get ambulance data from Vadodara. Bangalore limited ambulance data is available.
Sir, in terms of, sorry.
Just wanted to just write here catalog.iudx.org.
Okay, I'll just stop sharing my screen. Abhay, in case you want to share anything, you can please go ahead.
No, I've just sent it on the chat link that you can have a look if you want to the catalog and all the 18 cities and whatever data sets. I mean, the type of data is all available here. The private data sets are of course not available without consent.
Sir, I had one question in terms of the legality. In terms of these data are coming, from private cities and private citizens. So, is there any legality in terms of where in the cloud? I mean, can this be stored? Should it be inside India, or is it? It doesn't really matter where the.
Yes. Currently, so one of the things that we currently look at is we put only non-personal data. So we do not put right now any personal data. I mean, essentially, these are the techniques. Once we have a very good handle on DP, maybe we can say we can release this data under DP constraints. But right now, we handle only NPD. But even with non-personal data, we have strict concerns about the locality of data, and we can only deploy on what we call as those empaneled CSPs, cloud service providers. So currently, like Amazon is an empaneled this thing, and we take servers from the Mumbai cluster, and then they have agreements with the government of India that data will be stored in India. So there are 11 CSPs, cloud service providers. Only those we can use when we put the data out. Yes.
Thank you, sir. Thank you.
I have a question. I think the fundamental assumption while using differential privacy is that the owner of the data who creates this the noisy data set, right, is trusted, right? So at IIIT, we are working on a project on privacy preserving ride-hailing services, right? So now the idea is to the ride-hailing service itself is viewed as an adversary. Okay, I know that Uber employs differential privacy, but Uber gets to see the data, right? It might try to hide its data from its engineers, who does the analysis on that, or you make use of the data or other entities. But if there is no trust on the private entity itself, so you think that there are ways, modifications to DP which can handle these things, or it's currently out of reach of DP?
Maybe I can try to answer, and then maybe Dr. Abhay can add to it. So DP by itself, as you said, this was an important point, that we assume that, so DP also has two flavors. One is what we call as central DP. In centralized DP, the information from different users is noise free. So noise free information comes to the server. The server computes the statistics and adds noise only to the output. In that case, there could be questions raised regarding the trust that we are placing in the server. For handling that, secure enclave could be a very good solution. So use differential privacy together with the secure enclave. So the server should potentially be executing on a secure enclave. Here we are providing guarantee that the server will not leak your information to any third party.
Perfect. Okay, great. Yeah, makes sense. Yeah. And how does this translate to IUDX? So who is the trusted party here?
So currently, yeah, IUDX is the trusted party in the sense that, I mean, IUDX is a part of, per se, of the smart cities mission. So IUDX is a trusted party right now. And therefore, the data that we get is noise free. But then I think what we want to give out is based on the DP notions. Yeah.
Oh, nice. Oh, there's a question on hiring at IUDX. Maybe you want to answer that.
Please proceed.
Abhay,
I mean, hiring at IUDX is basically dependent on the projects and availability. I mean, if you are like for this particular project, this is a research project. So within IUDX, we have two tracks in some sense. So one is a very what you can call software engineering track, which is of course concerning how we are developing and deploying our platform. So if you have like good skills in programming, like the higher level programming, Java kind of stuff, and systems understanding, DevOps side, so then I think you can apply for those kind of jobs. And if you're interested in research, as I said, the feel free to write to us with your CV, and we will check based on whether we have any openings, and we can just have a quick discussion. Criteria is, as I said, depending upon what is the position. In the development side, I guess anything is fine, like BTechs are fine. But I think on the research side, depending upon whether we have a specific requirement where we are looking for somebody to develop a new algorithm, then maybe we need an MTech or a PhD. But if it is development, so for example, if we are looking for somebody to look into MPC framework, motion 2NX kind of stuff, then I think if you have good programming skills in embedded C++, then I think that should also suffice. Yeah. Just write to us, and I think we can talk.
So, and also I think for the participants, a good opportunity to interact with both the speakers. So if you raise your hands, we can unmute and you can directly ask your questions.
Maybe I just read through one of the questions that got raised here. The question was, what is the best tool or feature for data security? So as Dr. Abhay has told previously, we have different privacy mechanisms to protect data in different states. So for example, if you have data at rest, you just want to store something securely. So there are certain techniques, encryption techniques, for example. For data in transit, there are certain techniques. For example, practical protocols include HTTPS and secure FTP, right? Now, if you want to do secure computation, the problem with secure computation was, let's say there are multiple parties, they want their data to come together and you want to compute a function on data from multiple parties. Even if the data is encrypted at the input side, at the time of computation, this data was getting decrypted at the server, and therefore there was a threat that there could be a privacy breach at the server itself. To address that problem, there's one of the solution is a homomorphic encryption. We have seen that. The other one is secure MPC. The third one is a secure enclave. That is basically giving a software hardware kind of a system framework, which is assuring you that the data will not get leaked out of this hardware box that we call a secure enclave. And there's a trusted party that provides authentication for the secure enclave. For example, when Intel is giving out a box that it claims to be a secure enclave, Intel gives the guarantee that this box will not reveal any information. Of course, you need to write appropriate code. If the code itself has a chance of a side attack, then you cannot protect And finally, at the output, whenever you are releasing something to the public, at that point you want to add a little bit of noise to protect the privacy of individuals. And that is why DP is one of the techniques where you want to make a release to the public in general. You're not trying to hide that information. You have done some statistical analysis and you want to reveal it to the public. But you want to make sure that you add appropriate amount of noise such that the identity of individuals could be preserved.
Okay, any question? Shyam, there's a raised hand.
That's probably just noise. So it should be okay. I sent out a question. No, okay, now we have another raised hand. So, yeah, Jayasurya has a question. I'll allow him to talk.
Surya, can you just speak out your question, please?
Hello.
Yeah.
Can you hear me? I have another doubt that if we can able to hide our encrypted data in any file of the image or an audio video file, we can able to hide inside of this file for sharing of our data.
Yeah, so basically encryption will protect any bit stream. So any input, it could be speech, it could be image, it could be video. Finally, it boils down to a bit stream, right? You want to protect your data, and it's basically a bit stream that you want to protect. And the encryption will protect any bit stream. So it's applicable to any form of data. It could be text, it could be speech, it could be audio, image, or video.
Yeah, possibly the question is related to steganography, where you hide the data. Possibly.
Okay, thank you, sir.
So if there are no questions, Professor Vivek, I was just wondering that, are you doing any active work? I see that your research was related to homomorphic encryption.
Sure, yeah.
And we are looking at exploring few of the things, like we are not very sure right now whether you want to work on it or make a product, a prototype, but we are just trying to explore the feasibility of homomorphic encryption. So in case you have some platform or software tool which is providing options for engineers to use it in a practical setting, so that will be very useful, and we can engage. So that will be
yeah. Sorry, we could not meet in person. Maybe I think at least as part of the IUDX project, maybe we get to chance and it will be great.
Perfect.
So one of the latest things I'm working is on this, what is called this modular open source identity platform. MOSIP is a project where anchored at IIITB, right? And a lot of collaborators. And then, so what MOSIP project has done is configured, it's like Aadhaar, like identity platform, but it's open source. So for Morocco, for I think Philippines and then possibly Sri Lanka also, I tried to configure all these things for their use. So one of those aspects we are looking is how to achieve privacy preserving of this the demographic and data biometric data.
Right.
And so we are trying to use homomorphic encryption. We could come up with some practical thing, and then the MOSIP engineers are trying to use this, and then. So now we need to see where it goes. So
very nice.
I'm working on is this privacy preserving ride-hailing services. So
okay, ride-hailing service. Okay, very nice. Very nice.
So
yeah, so I think as a philosophy, like IUDX as an organization also is the fundamental principle is open source. So whatever we do, we want to reveal the code, the kind of techniques we use. For example, if we apply DP, we will release the code that this is the code that we use to inject noise, so people can have a look at it.
Oh yeah, yeah, nice.
So I think it will be very interesting to see how we can kind of work together.
So and also collaborating with Srinath on this IUDX.